When working with our inverse trigonometric functions, we focused on sine, cosine, and tangent. So with that, when we're solving these trigonometric equations, we want to get to that point where we're using an inverse function. So that means we want to get to a point where we're using inverse sine, inverse cosine, or inverse tangent. So with that, sometimes we're going to need to use our identities. So those reciprocal identities, so like cosecant, secant, cotangent, using the identity that tangent is equal to sine over cosine, as well as our Pythagorean identity. So these will be popping up and we'll make substitutions so that we can solve to a point where we're getting one of these three trig functions out, or inverse trig functions. So let's look at some examples. Again, we'll focus on grabbing our solutions just from 0 to 2 pi, and then also making that general formula to follow to find all possible solutions. So with this first one here, we have our equation. I can see we're working with secant here. And something else that's new with this one is that something's going on inside the parentheses. Something we could keep in mind is that this is a phase shift that's occurring. So in terms of our function, we don't need to worry about this too much. When we're going to start worrying about things will come when we're adjusting the period of the graph, which we'll see in a future video. With this, I could just keep in mind that the period, even with that phase shift, is still 2 pi. So nothing's really changed there. So in solving this, what we can do is first just focus on isolating our trig function. So I'm going to do is add 1 to both sides of the equation. So we'll have secant of x minus pi over 6 equals 1 plus 1, which is 2. Now what I want to do is adjust this so that I'm not using secant anymore. So I'm going to use that reciprocal identity, saying that this is equal to 1 over cosine. So this is the same thing as 1 over cosine of, and then everything that was in the parentheses before stays in the parentheses. So it's still of that x minus pi over 6 is all equal to 2. Now I want to get that out of the denominator, so what I'm going to do is multiply both sides by that cosine of x minus pi over 6, multiply by cosine of x minus pi over 6. So we're getting a 1 equals 2 times that cosine. And then just to isolate our trig function, I want to isolate cosine completely. I'm going to divide both sides by 2. I'm just going to adjust this. So cosine of x minus pi over 6 is equal to 1 divided by 2 from dividing both sides by 2. So we get a 1/2. And now I have the setup where I can switch to my inverse form. So I have this cosine is equal to a number, and what I can do is say that angle that's the input there, which is this total angle of x minus pi over, at some point I switch that to a 2, that should be a 6, equals inverse cosine of 1/2. Now, I'm going to put a pause on this x minus pi over 6. I'm not going to move anything yet. What I'm going to focus on is just replacing this inverse cosine. In terms of angles between 0 and 2 pi, what solutions would go there? And then our end goal is to solve for x, but what I want to know is what could I possibly substitute over onto that right-hand side of the equation based on inverse trig functions. So I have my unit circle. I have, let's see, we have an x coordinate of positive 1/2, which is about there. So we're getting that point and that point there. So we're getting these two sides. And in terms of angle measurements, we're seeing a positive pi over 3 and a negative pi over 3. Or if you wanted to count that as 1, 2, 3, 4, 5 pi over 3, that would work as well. And actually in terms of solutions for 0 to 2 pi, that's what we would need to use. So for now, I'm just going to use these two right here. And what I'm going to do is separate this into the two possible solutions that I'm seeing from 0 to 2 pi, because then it'll just be a matter of making our formula using revolutions about that terminal side. So I have that red angle and that green angle. Nope, I wanted to change my color there as I said it. There we go. So we could have x minus pi over 6 is equal to positive pi over 3. Or, from that negative pi over 3, that x minus pi over 6 is equal to negative pi over 3. And then it just turns into a little bit of fraction work here. So I'm going to add pi over 6 to both sides of the equation. And what I could do is think of this as 2 pi over 6. So let's see, we have x equals 2 pi plus 1 pi, so a 3 pi over 6. Which is pi over 2. So there's one exact solution. And if you think visually, that makes sense. Because what we were doing is, if you think about those wedges of pi over 6, what we did is we said inverse of cosine of 1/2 is landing here. Add on an angle of pi over 6, and that takes us to pi over 2. So we're going to do that same thing, but we're over here. So what I suspect will happen with that math is it'll land me at negative pi over 6 by that kind of addition of that angle measurement there. So I'm going to add pi over 6 to both sides over here. Again, that pi over 3 I could think of as a negative 2 pi over 6. So negative 2 plus 1 is a negative 1 pi over 6. So there we go in terms of our possibilities. Now for formatting our answer, so thinking in terms of 0 to 2 pi, we have that solution of pi over 2, or the angle that's coterminal with negative pi over 6, which would be our positive 11 pi over 6. So there's that form of the solution. Then I want to make my formulas. So with this one, I could use that more concise form of the formula based on its reflection over the x-axis. So I could say I either want to start at, actually I can't do that because this isn't really our end answers that we're visualizing here. These are. My bad. Really, we ended up at pi over 2 and negative pi over 6. So in making my formula for my answer, I can't use that symmetry because really we landed at these two spots and that doesn't have any symmetry. So I'm going to need to make two separate formulas describing like starting at pi over 2 and then just making revolutions around pi over 2. And same thing with the negative pi over 6 and making revolutions. Again, you could use negative pi over 6 or 11 pi over 6. They're the same angle, they're coterminal with each other, so it doesn't matter too much. So x is defined by that x can equal pi over 2 plus 2 pi k, or x can equal negative pi over 6 plus 2 pi k, where k is an integer. And there's that. So some extra steps there, just using our identity to get to working with cosine, and then we can think about our inverse cosine. All right, our next one here, and this is going to throw in a little bit of quadratic work. We're going to see more examples with quadratics, so we'll get a little introduction here. All right, so cotangent squared. I can't do much with that at this point. So what I'm going to do is change it to sine and cosine. So cotangent is the same thing as cosine over sine. Just make note of this is squared. So with that, this is going to be cosine squared over sine squared. So that exponent just carries through to both the numerator and the denominator, because it is kind of like the side work behind this would be that we're taking cotangent squared, and that would go to the numerator and denominator. All right, so that tells me that cosine squared of x is equal to sine squared of x if I multiply both sides by that sine squared. And then I'm kind of stuck. I don't have much to do here. And what I'm really struggling with is that I have two different trig functions here, and I only want one. So what I'm going to do here is use the Pythagorean identity. I want to make a substitution so that I'm only working with sine or only working with cosine. Now, in terms of which one to replace, doesn't matter. We'll end up with the same solution no matter which one. So meaning I could either go substitute here with a 1 minus cosine squared, or substitute here with a 1 minus sine squared, and it will work the same. What I'm going to do is substitute sine squared with 1 minus cosine squared, just because I like cosine. No real reason. You could go the other route and see if you get the same answer out. So with that, if I know that cosine squared of x is equal to 1 minus cosine squared of x, then I'm going to go ahead and add cosine squared to both sides. So that'll leave me with a 2 cosine squared on the left-hand side, and I'll just have a 1 left over there. Divide both sides by 2. So we have a 1/2. And I can't take the inverse yet because of that exponent of 2. So what I need to do is get cosine all alone on one side of the equation, but I need to get rid of that exponent of 2. So this is like if we were solving an equation and we were left with x squared equals 1/2. Well, what we would do is take the square root of both sides so that we would just have x. And then this is our square root property. Whenever you take the square root of both sides of the equation when you're solving, we always get that plus or minus in there. So we're going to need to remember that here. And again, we'll see more of these with our quadratic practice. But this, 1 over root 2 that we're working with, or root 2 over 2 if we rationalized it. So we're going to do the same thing. It's just we're working with cosine instead of just x. So what I'm going to do is take the square root of both sides, so that then I just have cosine of x equals, and then I'll have a plus or minus since we took the square root of both sides, and then that 1 over root 2, or if we rationalize that, root 2 over 2, and then we can form our inverse cosine. So this is going to look a little weird, but how I'm going to write it is that x is equal to the inverse cosine of plus or minus root 2 over 2. And we go to our unit circle. Now we haven't seen this before with the plus or minus, and we could even write this as two separate cases. If you wanted to write it as x is equal to inverse cosine of positive root 2 over 2, and then have separately or x is equal to the inverse cosine of negative root 2 over 2, that absolutely works as well if you wanted to expand it out. Visually, on our unit circle, what this will look like is, so we're working with cosine, so these are the x coordinates. So we could have x coordinates that are positive root 2 over 2. So those are happening at our increments of pi over 4. Or negative root 2 over 2, which is still our increments of pi over 4. So we end up with 4 angles here. I have 1, 2, and 3, and 4. Now what I could notice is that these are my increments of pi over 4, so there's my just positive pi over 4. Then let's see, 2, 3 pi over 4, 4, 5 pi over 4, 6, 7 pi over 4. So right there are my possible solutions for x on 0 to 2 pi. X can be pi over 4, or 3 pi over 4, or 5 pi over 4, or 7 pi over 4. All right, now for the formula here. Now the period So the period of cotangent is pi. It gets a little tricky when we square it. So let's just work visually in terms of what period are we working with. Now what I could notice is that between each of these is a 90-degree angle, or a pi over 2 distance. So what I could do is I could make a formula saying we can be at pi over 4, and then any increment of pi over 2 away from that. We have 1 pi over 2, 2 pi over 2, which is just pi, 3 pi over 2, and then 2 pi would bring us all the way back there. So just recognizing the symmetry of this, of how we're just making those jumps by pi over 2 each time. So my formula, I'm going to say, is x is defined by that x is going to be equal to, I'll use pi over 4 as my starting point, and then plus any increment of pi over 2 away from that point, where k is an integer. And there we go. So with that one where the period can be kind of tricky to see, just look visually and you can see the jumps that you need to use.